Hello, this is a rundown of project number one. And in this project, a performance run will be conducted to test out two different data structures that manage process control blocks. The first version will use an array list or a linked list and will dynamically allocate, deallocate memory to handle processes and subprocesses. The second version will use what I call sibling pointers, pointer arrays. It doesn't use any kind of dynamic memory management and should in fact run faster with less overhead and be more efficient. So next, I'll demonstrate the actual running of the program. Before getting into the demo run, I wanted to really show here in project requirements the difference between these two versions. Version one uses a linked list or dynamic array to keep track of child processes. And version two, what's different about it, it doesn't even use an array list. Instead, it uses these four indices: parent index, first child, the younger sibling, and the older sibling. So now let's get ready for a demonstration of the run itself. In this case, I'm using Java language in the NetBeans IDE. First thing here in the main function, we call a test function in main that passes how many times we want to loop around and run the test and which version we want to use. Version one of the PCB data structure or version two. A timing value comes back for each case, and then we take the difference, and between that difference, we can tell which one runs faster, which one is slower. The test function itself is where we call with the version number, we call the process control blocks. That is what handles the main management of the PCBs. One uses again the array list, and the second one here uses the sibling pointers. We loop around a million times creating processes, and then we destroy all those processes, calculate an overall time, and we pass that back to the main routine to report those times and take the difference. So in here, I'm going to show, I'm going to compile and run it. And as you can see here, version one used 135 milliseconds, version two, 68 milliseconds, and version one runs 67 milliseconds slower, as we anticipated, since it uses dynamic memory management. Well, here's a rundown of version one as far as how things are being managed and in a PCB table and also in a process tree. And I think the easiest way to uh, fill out the process table is by looking at the process tree. Over here on the left are the PCB arrays calling the create function several times to create processes and child processes. So starting out, PCB 0 is initialized with the parent of -1 and an empty array list. Version one only has those two data members, the parent and the array list. And process 0, that's the Atom process. All other processes are descendants under that. So with this first couple of calls under process 0, I create a child process 1 and 2. That's why the parent index is 0 in each case. Right here from the process tree, you can see that one doesn't have any children, therefore its array list is empty. Process two, though, has two children, which is at 3 and 5. And as I continue down here, uh, as process two is created, you can tell that it's as process three is created under two, its parent is 2, and under process three, it has a child process of 7. Even if we work all the way out here to the end at child process 8, it has no children, therefore its array list is empty. And you can look right here from the tree, process tree, that its parent is 7. And essentially, this logic applies throughout all of these processes in filling out the process table. And that's pretty much the rundown of version one PCB. Okay, this is version two of the PCB. And again, I've got a process table and a process tree. And the only way to really be able to visualize what's going on is to have that process tree available to show the correspondence between these two visuals. The difference here between version one and version two doesn't use an array list. It doesn't implement any kind of dynamic memory allocation. Instead, it uses sibling pointers. In particular, it has four: the parent, first child, younger sibling, and older sibling. As an example here of one that's filled out pretty completely, which is subprocess two, child process two. As you can see from the tree, from the process tree, that two has as a parent zero. And so right here, you can see under child process two, its parent is zero. And as a first child, it has three. Um, Also under this, when I created process two, guess what? Process one was created earlier, and therefore one should be my older sibling. And sure enough, there it is. And subprocess four was created after subprocess two. And therefore, since it was recently created, that would be the younger sibling. This type of logic applies all the way across for all the subprocesses, child processes, even here all the way out to eight. As a child process to seven, its parent is seven. It doesn't have a first child because it's by itself. It has no children. And because it's by itself, it has no other siblings. And that's why it's marked as -1. Initially, before this process table is even created, PCBS at process zero, again, it's the Atom process and all other ones are created underneath it, and it's initialized to -1 for each one of these data members. -1 means I don't have a parent, I don't have a first child, I don't have an older or younger sibling. And that is pretty much how version 2 PCB management is being handled at a high level. So now I'm going to go over version one, a high level overview of version one create and destroy methods, probably the most important methods in the entire program. For the create function, it's kind of shown here. I'm not going to go through it line by line, but just high level, the method simulates the creation of new child processes under an existing parent. And it finds an available slot in the PCB array or process table using what's called a circular array. It creates the child and links that to the parent's list of children. This right here in the while loop is that circular array, and it searches around for an empty slot. It goes to the very end, it wraps back around because it knows the total number, and it uses the modulus operator to help it figure that out. Likewise, here for the destroy function in version one, it recursively removes all children and descendants of a process P. I've got a destroy method here that if you bury down, you're calling destroy again. So a function that calls itself is recursive. It frees up memory in the slots in the PCB array. It cleans up the parent-child relationships starting from the first child of process P. It will recursively destroy each descendant one by one. And this mirrors how an OS system would clean up child processes when a parent is terminated. Okay, version two of create and destroy methods involves a little bit more work. For the create function, it starts out just like in version one. It uses that circular array once again to find an empty slot. But at a high level, the method basically simulates the creation um, of child processes in a tree-like structure. And instead of using a dynamic list like in version one, it uses direct pointers because it knows its first child, its younger sibling, and its older sibling. If it has no children, it will simply set its child pointer to a new process. However, if the parent already has children, it'll walk through the sibling chain to find the last child right here in this while loop. We can link the new child to the end of the chain, setting it to the older sibling and updating the previous child's younger sibling pointer. In this process, it uses a previous index to track the last child in the parent's child list, the one that will become the older sibling of the new child that you're adding. And in the destroy function, it simulates the termination of child processes under a given parent. It walks through a parent's child list recursively, deleting each child and their descendants as well. It clears out the parent's child pointer. It's like pruning a tree and clearing out the branches off the tree. It starts out by checking to see if a process exists. And if it doesn't, then there's nothing to destroy. Next, the parent's first child is used as a starting point for the destruction process. We basically, in this while loop, we loop through all the children of process P one by one using the younger sibling pointer to move through the chain. And for each child, we first destroy its own children recursively, and then we remove the child itself by setting its slot to null. And that ensures we clean up the entire subtree. In conclusion, in comparing the two PCB management techniques, we found out from an earlier prior demonstration run that version one was slower by about 67 milliseconds. And that's mainly due to the dynamic memory management that's incurred by using an array list or linked list over uh, regular array pointers. And that concludes my overview of Project One. Thank you for your time.